Welcome everyone. My name is Daniel Howard. I'll be presenting on verifying code correctness with PCAST. This will be a session focusing on the mini weather application again. We'll be using specifically that PCAST tool, which is a parallel compiler assisted software testing. We'll first go over the benefits and challenges of validating scientific software. PCAST is one of those tools to help enable that process. And then we'll go through the actual execution and using PCAST as well as in two different modes of operation, one being with a Godin file and one with OpenACC and autocompare. So as before, here's the workshop etiquette. Feel free to update your current repository with the GPU workshop materials for today. We had released last week the mid-workshop series survey. Please feel free to head to that form there that's linked in the presentation today in order to fill out that information for us so that we can improve upon our sessions for future workshops. So for today, we have our similar setup as before, set up our project code for our project we have in the workshop. Today, we should have the you can either use the Casper queue if it's, but preferably, again, use the GPU workshop queue. We should have gotten that fixed this week for you this time. Either way, if one doesn't work, feel free to switch between the two. You just have to change the text here between GPU workshop or Casper. So let's talk first about the benefits of validating scientific software. So building trust is paramount for the effective sharing and receiving of computational software. So here's a diagram that's produced from a NASA workshop a while back. Basically, the concept of verification and validation, that does fall within a few of these boxes here in terms of enabling transparent, accessible, and inclusive and reproducible science, specifically transparent and reproducible science. Basically, if we can verify that and validate that our software is in fact working to specification and in fact correct to what we expect it to be doing for the science that we have programmed into the software, that is in fact improving the same, enables showing that our work is in fact transparent and thus then reproducible for other researchers to work on that same software and as future developments are added on to the software itself. So speaking specifically on reproducibility, the better we can enable reproducibility through ensuring and showing that, in this case, with PCAST, that it's verified and validated, that builds greater trust in the system. So greater trust in the accuracy of scientific codes enhances that reproducibility goal we have in mind for much of our modern scientific codes and ways in which we're publishing data within the scientific ecosystem. So, and here we're focusing mainly on, you just want to get the code out there. Then you want to, if you even better, you include code and documentation and easy installation, and as well as being able to reproduce the environment to run that code in. Within those kind of products are the same thing of processes for testing and verifying that the software is working in the first place. That can include unit testing, but in this case, we're focused on this easy accessible tool of PCAST for showing these reproducibility standards in more accessible ways. If you want to learn more about promoting and utilizing open science best practices, feel free to follow along to any of these links here provided on this slide. So one part of the major issue when navigating scientific software development is, whether you like it or not, I have always introduced bugs into my code whenever working on new algorithms or ideas being added into the software. So it's important as we are making these changes and additions to software to make sure that those bugs are in fact we're made aware of them and we're in fact dealing with them. So on average within industry software development, this could be in the range of 1 to 25 errors per 1,000 lines of code. And we can recount specifically an example of some negative outcomes when bugs are not determined ahead of time or in an appropriate fashion throughout the software lifecycle. So in this case, let's look at this modeling protein structures model that was done by Geoffrey Trang. You can read more about it in that ISC presentation given by Anshu Dubey. So in this code, there is an inadvertent introduction of transposing of columns of data for electron density map. In that particular case, the model then produced an incorrect protein structure. It ended up leading to the retraction of 5 publications, and one of those publications having many citations. Other papers and grants that conflicted with the result were then rejected. Chang ultimately did find and report the error himself, but that causes a lot of back and forth and having to deal with that error in the first place over the time of that software. And it would be better to come up with a process to deal with these errors throughout the software lifecycle, as opposed to at where things go wrong. So if we can build in a process that includes ideas like unit testing, or in our case, we'll talk about PCAST, this is vitally important towards avoiding such issues where bugs can be introduced. So as I'm saying specifically, PCAST does not do unit testing as that might be known to you, but nonetheless, it's still an important tool that can still enable different ways to verify and validate software. If you want to learn more about the broader landscape of reliability of scientific software, feel free to refer to the Better Scientific Software Organization and some of their blog posts that they have on their website. So there are challenges involved with invalidating scientific software. It's not just, does not always just pose to and benefits to doing this extra work. Of course, it is extra work, so that's one kind of challenging part of it. But nonetheless, given the nature of scientific software, it's constantly changing. So there's many ways that you have to constantly be thinking about towards adapting your validation workflows to manage the ways in which that scientific progress and new algorithms, new ideas are rapidly implemented and introduced into software. There's a paper you can read here about that particular framework within the computational material science community that I think highlights some of those issues pretty well. So to go over some of those issues that occur within validating and verifying scientific software, basically we lack precise oracles. What I mean by that is that whenever we're coming up with, doing research in a space where, research is research, we don't necessarily know what the end goal of the output data is going to be. Knowing the precise output of a science or engineering model is typical and impossible a priori. Additionally, especially within the engineering space of how computing computational arithmetic is performed, IEEE floating point computations are inexact and can change depending on operation ordering and type. If you want to learn more about that IEEE arithmetic and those sort of issues you might want to learn about, feel free to read that paper about floating point arithmetic by David Goldberg there. Another issue is a large configuration space. There's many, due to the nature of scientific software, as I said, there's many different algorithms, approaches to problem solving, and thus that complicates the space of how we go about testing and verifying that different approaches are in fact staying correct and still within our scope. And each time we may add a different algorithm, we might need to add a new test, and it's constantly a struggle to keep up with the changing environment as software is being developed. Another issue to think about is, a lot of our models working on, especially in the earth science community, is we have large scale and heterogeneous data. Selecting test and validation data at pre and post testing steps results in high data variability. It's very difficult to test across these large scale data objects and computational metrics that we're in fact, putting out there as each of the model is running through its runtime. If you were to try to test, say, the full, global scale model to make sure that it's producing the same output from run to run, that is a significant cost and very cumbersome to manage, say, in a testing environment. So you have to think about ways to manage smaller scale problems in order to deal with not burden yourself in terms of these large scale kind of data management issue when thinking about verification validation. Another last issue to think about is global software development. In this particular space, you can think of especially in modern scientific development, we work across many different teams, across many different places and localities, and even just divisions within your workplace. How to coordinate those teams across different places and different time zones, perhaps sometimes, is difficult. And coming up with a standardized testing framework across those teams is not only difficult just for the sake of developing the technical aspect of that, but also can become a political process and navigating the different ideas and ways in which that's meant to be approached. And saying all these, it's not to minimize and say it shouldn't be approached in terms of performing verification validation on your software, but nonetheless, it's important to think about these issues as you're navigating the software development lifecycle of whatever project you might be working on. So getting into PCAST, again, PCAST stands for Parallel Compiler Assisted Software Testing. So within the NVIDIA HPC SDK, this is where the PCAST tool specifically lives. The PCAST is not available within other compiler suites. This tool serves as a convenient compiler-aided framework for quickly building in some level of software testing into your development workflow. Essentially, there are quick flags and additional and small changes you might need to make to your code in order to enable this PCAST testing framework without necessarily needing to go into the more in-depth process of a larger scale unit testing framework. This is not to say that PCAST will cover everything you need in terms of validation of your software. Thus, if you want to go actually cover all your bases in terms of making sure your software is performing as you imagine it is and want it to be, that will involve some additional approaches like unit testing, which will not be covered today in this workshop. So there are two approaches that PCAST primarily allows for verifying software. Either it uses output from previously run code and checks to make sure that it's similar or equal to the output of then modified code. This is using a framework using what's known as a golden file. It can also do an approach looking with such that the calculations of the CPU is made sure to be similar to or equal to the calculations then performed on the GPU. The nifty aspect in terms of GPU computing using OpenACC is that basically the CPU code remains untouched. So the compiler is able to compile the CPU code in the same way without the GPU code at the same time of compiling the GPU code. And you can run concurrent program runtimes that are, one is on the CPU entirely, and one is then going back and forth on the CPU and GPU, launching threads and returning data back to the GPU back and forth, just like you recall from previous sessions and how OpenACC does this process. To remind you of kind of like process pictorially, say we have a CPU code and you have a data copy in region, data copy out region, and it goes under the GPU there, and like that's typical runtime of a GPU program using OpenACC, using CUDA, using whatever framework you want. Within PCAST, though, essentially what we can do and what PCAST enables is it sees whenever that data copy out operation is performed, it can compare and report differences between the data that's then on the GPU and the data that, say, was allowed to redundantly run on the CPU. This allows for interesting ways to maintain a verification suite within the GPU programming paradigm and ensuring that whatever code that we developed for the GPU is in fact doing the same things that we thought it was, we know it's still doing on the CPU. So as I said, there are two main usage approaches for PCAST. The main documentation for PCAST can be found on NVIDIA's HPC SDK site under its HPC compilers user guide. Feel free to refer to that for a more in-depth discussion and all technical details of how PCAST is implemented within the compiler. You can also refer to a specific blog post that details this again in a more casual, kind of readable manner on NVIDIA's website. So that first approach that PCAST can use for verifying software is basically run using a golden file. So in a golden file case, you can add calls to your program or add directives, either PCAST compare or using changing from the exclamation $sign ACC, you're going to instead use NVF here for compare. And basically this allows you to then, at each time you encounter those directives, it'll then compare the results of whatever's on the CPU at the time to what's then in the golden file that you may have done in a baseline run earlier. To note that if you use a directive approach, you just have to enable that with the -m PCAST compiler flag. And so there's a way in which to navigate that the golden file procedure without necessarily needing to modify the source code itself. It can keep to only adding in a sense comments or directives that only get enabled if for specific compiler flags you might add at later times when you want to do this testing. The other opportunity is with just keeping your same OpenACC code you already have, and you can then either augment that with additional ACC compare calls or ACC compare directives. And then you can either then add the compiler flag GPU redundant or GPU auto compare to essentially make those comparisons through the OpenACC runtime. This might not necessarily require additional modification to your code, and will essentially compare the results of your CPU and GPU data anytime that data is moved from the CPU to the GPU or vice versa. That process, if you want to compare at additional places, the addition of those calls to ACC compare or the ACC compare directives will enable such additional opportunities for comparison. There are additional options that can be set with this PCAST compare environmental variable, and we'll go through a few of those options there in a little bit. So let's first start with usage of PCAST. So with the golden file. So in this approach, PCAST can be run comparing successive program runs against a ground truth golden file. So essentially, CPU results will be compared to other CPU results with the assumptions that the results in the initial golden file are correct. So even though we're talking about GPU computing, you can still run this and then as a golden file, and then so long as your data management is going smoothly and you're confident in that what data is on the CPU at the time is appropriate, you can still set up a golden file type run with a GPU code that will compare the results between a baseline run of your code and then any future minor modifications to it that you don't expect should be changing the actual results of that model. But it's important to keep in mind for the golden file method that you're always comparing CPU data to other CPU data. It's still up to you to determine whether or not that CPU data is in fact correct in the first place. So that's more of a scientific problem, and making sure that you've done other more robust unit testing throughout the development lifecycle of your model in order to ensure such confidence in the CPU results themselves. So again, with the golden file case, you're going to be using the PCAST compare function call, or using the NVF compare directive in order to navigate usage of a golden file. Essentially, the first time you run such a program, once you add those directives into your program, it will then create that PCAST compare data file known as the golden file by default. And any subsequent ones will find that data file and then compare the data that's being produced at these same moments in time where the PCAST compare calls or NVF compare directives are found, in order to ensure that the results are staying the same to the original golden file as produced. Notably, the directive approach is much easier to use compared to the PCAST compare function call. And that'll be evident within the next slide, in the sense of the prototype of the PCAST compare call is just rather large, but it does allow for like more fine-grained control of what's being put in that golden file and how those comparisons are being made. So in the PCAST compare call, you have essentially 7 arguments you do have to navigate. Basically, the variable you want to end up comparing, the value type you want to end up, and data type you want to be comparing, which has got to be a real number, an integer number, and a complex number to varying degrees of precision, as well as then the size and the number of elements to compare within that array for the data variable you want to be saved and or compared. Beyond that, you're able to then add in, say, descriptors about that specific object you're going to be comparing, including, say, the name of the variable itself, the name of the source file it's in, the function that's in, the line number. But admittedly, all of those can be whatever you prefer, but that format is essentially what PCAST essentially formalizes in terms of encouraging accurate tracking of what differences are occurring where within the code. So there are additional PCAST options, as I mentioned, to the environment variable. You can then also specify a specific data file name for the golden file. Basically, if that file doesn't exist and you run with the PCAST flag present, essentially, if the data file does not exist, it'll then create one, and then each subsequent one, seeing that it exists, it'll then compare it to that golden file. If you would rather explicitly force the creation of the golden file or explicitly force the comparison of that golden file, you can then say add to that environment variable list of options the create or compare flags. If say you want to just, if you've kept the program compiled with the PCAST option flag, you can also just disable any of these functions from actually having any effect at all by just adding the disable option. Note that this would not impact if you have the GPU redundant execution enabled on for an OpenACC code. So you still have that whenever you have that redundant operation happening, the CPU code and GPU code are happening simultaneously. Ideally, the GPU code is running a lot faster than CPU code. So whenever you have the GPU redundant option on, your code should likely slow down a lot. So just because you might add that disable function, or if you want to say get out of a testing environment, the GPU redundant option will still significantly impact the performance of your model if you in fact have that also enabled. The whole list of the PCAST compare environmental variable options can again be found in the NVIDIA documentation. So as for our first exercise, let's just create a golden file using PCAST. So going back to many weather as we had before, we have in our folder a OpenACC or original Fortran 90 source file that we'll use, and then we'll create a original executable associated with that to make our essentially baseline golden file, assuming that particular run is in fact fully correct. We can essentially to do this, we want to add a few directives. I'm going to use directives in this case since that's just easier to navigate. But you can also use the PCAST compare calls if you like, so long as you have the use OpenACC module heading at the top of your program and following the function prototype detailed earlier. So a simple recognition here in terms of this exercise is just basically save the results of the state variable into the golden file near the end of program execution. And that way, in future runtimes, we can simply just compare that state variable to future runs of that state variable, and basically making sure that our runs are in fact deterministic and staying constant for each time we run it, and maybe mild modifications you might change, and hopefully then avoiding any bugs we had then introduced. So to do so, let's go back to our our workbook here. So yes, we want to create a golden file, and we want to use these two cells in order to do so effectively. But first, let's open up the file here. Let's close out some of these extra ones. And basically, what we're going to do, we're going to have at the beginning of our program, you might want to, if hopefully you're relatively familiar at this point with Miniweather, we have our main program that starts here. And then from there, let's say we just want to check the value of the state variable, as we just said, with the golden file by writing out the state file to the state variable to that golden file around the end of the runtime of the whole execution. So here we're just adding this directive here with NVF state, and this basically just tells the compiler that when we reach this point here, it's going to take the data that's on the GPU and basically write that out to the, actually it's going to take the data that's on the CPU, keep that in mind, and which is important here as I wrote it. Actually, we want to move this outside of the data region, because just in case there's a copy out that happened, which I believe it does, we want the accurate data from the end of the model to be reported in the golden file. Invariably enough, we could add that directive really in many other places in the model, or even test for different variables in terms of and checking for accuracy or doing more a refined analysis in terms of isolating a specific change in a variable or maybe a specific bug. But in this case, we're just going to look at the state variable here, assuming that the overall runtime of this original mini weather model is in fact still correct. So that's the only addition there we're having for this golden file creation process here. So after doing that, I believe before I do that real quick, I want to quickly go back to the top here and make sure I run our initialization of a workbook here, GPU workshop. So if you haven't done that already, make sure you do that. And then, I have to put this, don't forget to change this to GP 100. And then head down to that section again. We can compile a model, see unrecognized PGI directive. So I may have typed something incorrectly there. It should be correct, I think. PCAST was working earlier, 148, right? ACC and data. Let me just say that one more time, double check. Live debugging is always kind of fun sometimes in workshops. So, okay, so it's in fact in the, I left out the keyword here. Feel free to chime in or chat and let me know that when I'm missing things like that. It's important to keep me on my toes. Yes, so basically, it'll compile that program there and incorporate that call to create the golden file there. And then we can, this create file here is not important in terms of if the golden file already exists or doesn't exist actually. But if you want to just force the creation of the golden file, you can just add that PCAST compare here and make sure you then pass it into the job environment in order to make sure that you're actually then creating that golden file. So when we run this job, and hopefully it goes through relatively quickly, if not, I can always go back and change the queue we're in. So it looks like it went through right. And you can see that this PCAST compared that file got created. So that is our golden file that we just made. It used the default file name PCAST_compare, but you're welcome to change that file name to whatever you want with the earlier environment variable settings that I mentioned. So having done that, any questions about that process for creating a golden file? So, okay, moving on. Let's go back to the slides here. For the next exercise, we're going to basically have then now taking that golden file we just made, we're going to test against that golden file. So now we're going to go to the unoriginal many-weather MPI OpenACC code here, and we're going to introduce a bug to that code and see how that influences the outcome, the results, and basically what PCAST is able to find as being the error within that code. So if we go back to the notebook here, we can then see this new set of cells to run. These will then be pointing towards the OpenACC file, not the OpenACC original file. And let's double check just to see. Maybe let's go in and like add in some random errors somewhere. Maybe like we forgot this minus sign here. So let's get rid of that minus sign. But keep in mind, we do need to add in that original basically call to the golden file creation process within PCAST using this MVF directive in order to have the same comparisons being done at the same place within the code. So you see here, we just basically add the same thing we did in the original version of the code, but both in the same place. And essentially, when you're using these golden file kind of comparisons, you want to make sure that the changes you're making that's say encouraging you to do this validation test in the first place is incremental enough that where you're in fact doing the comparisons does not change between the different files, so to speak, or the different executables you're rerunning. So if you make significant changes to your file and then you end up, say, comparing different variables, your PCAST is not going to be able to reconcile the differences of the data stored in the golden file. So having had done that, let's now recompile the new program with the error introduced. You see we got rid of that negative sign there. So there'll be some slight differences as we see. So here we just have this compare now instead of create. And I just added this summary flag here in order to just have a summary printed out at the end of the comparison done to see what different differences are. To note, I also have a really short runtime, just a simulation time of 2, output frequency of 1. We're not doing much computation wise, but that's still enough for us to see where some divergence can occur. So when we now run the new code with the enabling the comparison to that golden file, we see that well, actually there's no errors found in this one. So maybe that negative sign was supposed to be there in the first place. Or let me double check if I'm building the right one. And we have, this is the original. We were at, where did we change? It was a flux change where I got rid of the negative sign. Yes, it was here. So on 314, I got rid of a negative sign. I think I had, let's see. So in that case, maybe I didn't save it. So let's just try rebuilding it. Pretty sure it should show some sort of error because it's obviously a significant difference if you lose out a minus sign. So again, it's like not finding errors in this case, old values, new values. So maybe it wasn't let's see. You can always introduce even further errors into this. Let's just do like, just maybe, maybe get rid of maybe like square this U or something like that. That would I think that would obviously change something. So if this is the fun part in terms of live coding, all these sort of things. It's difficult to navigate the exact determinism of all the changes you might make. So maybe I'm compiling the wrong one here. Because I see it's doing the comparison here. And nonetheless, it's not finding any errors. So I might have to, if we have more time at the end, I might go back and just check that later. But the process at least makes sense, hopefully, in terms of that sort of a framework. There just might be a slight typo somewhere in terms of which output file I'm processing in this particular case. If you see it, yes, someone, Koichi saying I'm getting data file PCAST compared file not found. You want to make sure that that file is either present in the same working directory you're in, and or there are sometimes issues within how the Q command job submission process works. Will that file be end up written out to the root directory? So here sometimes my output file gets put here, but nonetheless you want to double check that maybe there's some inconsistency there. But if it's not found, basically you want to go back up to the creation of the golden file process up here from the baseline model and making sure that it's in fact doing what it needs to do there. Yeah, apologies for the minor issue there in terms of the showing the difference between the two, but essentially, if there was no difference, you'd see something like this, and that's a good thing. In this case, I'm expecting a difference, so it would show something different in terms of the various errors you would see when it's making that comparison. So that's we might jump back to that really quick at the end just to double check why that's happening in terms of my earlier tests and not getting the same results. But in any case, any questions so far? The one that's admittedly more interesting, and I think probably more useful in terms of GPU development, will be using of PCAST with OpenACC and then the GPU redundant and auto compare options. So basically, for these approaches, PCAST can now be used also to compare directly the calculations that are on the CPU and the GPU. So as I was explaining earlier, the program runtime can redundantly run the code for CPU and GPU at the same time, and then end up compare the results that are achieved on the CPU and GPU distinctly to each other at distinct points within the code as specified by when that data is either moved either through the auto compare option when you're already moving data already through just the way in which you manage data through the development of the program itself, or through your own manual addition of ACC compare flags in order to directives in order to do that comparison at specific places where you might want additional reassurance that the values are in fact staying the same between the CPU and GPU. So notably, the auto compare option is the easiest method to quickly test correctness between CPU and GPU code, particularly when using OpenACC, and in this case, it automatically implies a redundant operation. So when you're running, when you specify auto compare, you're essentially forcing that redundant mode where you have CPU code generated alongside GPU code and ran redundantly side by side. Whenever then in an auto compare mode runtime, essentially, whenever you encounter a data movement operation, that is when the comparison will then take place. So essentially, this helps to identify whenever a particular OpenACC implementation might be causing some form of divergence or incorrect answer in your GPU code. So this might be specifically like missing a private directive and not specifying like certain variables should be made private to each thread across a GPU kernel, or perhaps a reduction clause is missing, or maybe there's some other issue in terms of like bad management of data movement within the model. So the auto compare option helps facilitate the identification of an error within a particular GPU kernel. Again, just to highlight some additional PCAST options here, you can specify a output to place all the basically PCAST printing, basically logging to a specific file rather than to the standard error stream. So if you'd like to do that, you just use the output file equals the name of the file you want to use or the path to that file. Again, you can use that summary directed option that we used earlier in order to print a summary of the comparisons at the end of execution, rather than each individual error being printed out line by line. If you also want to say go by the absolute or relative or ULP difference, that's the unit least precision difference between the values, you can use these different ways of computing basically the metric of how you're looking at the difference between variables on the CPU and the GPU. These options also apply for the golden file operation mode. So feel free to apply them as needed for either approach you plan to use. You can also use the IEEE option if you want to enable not a number of checks for basically the scope of validation that you want to be doing. For the report variable, say you have a very large matrix or array you're comparing, ones that's like thousands and thousands of elements. By default, every time that there's a difference, and oftentimes if there's a difference within a matrix, there's many differences within that matrix. There's probably something inherently wrong across all the threads that are doing those modifications there on the GPU for that operation. So by default, whenever it encounters that difference, it'll print 50 of them all at once, and that can basically just become a chore to sort through. So you want to just if you want to modify and limit the amount of differences reported, you can always set report equals n to a lower number as needed. If you also just want to stop at any first difference encountered outside of the tolerance specified above, you can just add this stop variable as well. Again, the full list of environment variable options can be found in the NVIDIA documentation. So going on to our next exercise, and if we get through this quickly, we can try to debug the last one. But nonetheless, let's go ahead and go through using PCAST with the redundant and auto compare options. So with auto compare, when we implement this in a little bit, you notice that many more errors will actually be reported. However, a lot of them are within machine precision error, as you'll see. And this just can be related to just the different ways that GPU and CPU code ends up getting compiled, and the mild differences in terms of the arithmetic that's being done between the CPU and GPU that can cause sometimes small amounts of machine precision error between the two devices. This is sometimes a problem, sometimes not. If you want bit-for-bit reproducibility in GPU code, that's sometimes a difficult ask in terms of what operations are in fact being done on both the CPU and GPU. But this option, at least, if you want to achieve bit-for-bit reproducibility, you might say leave out the tolerance variable here, the ABS equals 12, for example, in order to further refine and maybe like do some very in-depth or complex ways to mitigate such machine precision differences. But nonetheless, in many cases, GPU computing, it's in fact acceptable to be okay with a small amount of precision error. Obviously, though, if you get an error in a much larger degree of magnitude, then you'll want to say do some further investigation to see what is in fact going wrong. And to clarify, in this case, of which we'll do in a little bit, when we add the ABS equals 12, that's basically saying we don't care about error that's less than 10 to the minus 12. You could maybe even add 15 there, and go closer to the actual like double precision limit, 10 to the minus 16 or so. But nonetheless, this tends to be appropriate in terms of our case, in terms of seeing where a large scale errors accumulate. It's important to note, at least especially for weather and climate codes, a lot of them are nonlinear chaotic. So if you let the model run for a long time, some of those errors can accumulate, but in general, they still shouldn't diverge too far from the CPU code. But that'll be up to your own judgment in terms of determining what is appropriate in terms of your verification validation needs. So let's again go back to our notebook here and go to this next exercise. So basically, we can just run this auto compare clause with, we can keep the same code we had before, add auto compare, and it will then change, it will then do the auto comparison without necessarily any further additions to a model or source code in order to do that verification validation. So as you see here, we have we still have the golden file kind of directive we added here, but that is not relevant for auto compare, and so that will actually end up being ignored. I'll actually end up just do some Control Z and undoing the errors I introduced earlier. I'll keep that golden file directive here in order to just keep it consistent. But nonetheless, this is relatively the same to our original file. If we like, we can even say, let's just do a, well, as that's compiling and running, we can see what it's doing its thing there. If you like, we can just add a quick, as it'll print out all the errors it's seen between the, specifically it sees errors between the sendBuffL function. Initially, it's the initial values appears to be 0, and then it differs like 10 to the minus 17. But in this case, these differences are not as significant as we might think. And so you might think there might be like a lag going on between the sendBuffL and the when the CPU is computing the data and the GPU is computing data, and thus they're not aligned properly, and there might actually then be a bug within the code. But in this case, it's just a quirk of how the variables are being declared on the GPU and then operated on the CPU versus on the GPU that's introducing these differences. And as you can see, these differences on the scale of 10 to the minus 17. So they're actually not that significant. They do accumulate a little bit over time, if we let it run longer. But our conservation of mass and total energy is in fact, as expected, and I don't think here that there's a significant error in the program. So if we actually wanted to get rid of those issues, as we see, and basically allow the PCAST to ignore that problem, we can add that ABS equals 12 there. So any difference, absolute difference, that's less than 10 to the minus 12, it's not going to report that this time. So when I rerun this section, we'll see that now there's no problem reported. That summary clause here still printed out some of the tasks that the PCAST is doing here. So it basically said, it compared 46 blocks, essentially, 46 times, and encountered a data movement clause that it wanted to do a comparison on. As I said, autocompare just automatically does that for you whenever it reaches a data movement clause. So the main movements, if you call from within mini-weather, whether it's the moving of the send buffers and receive buffers between CPU and GPU, and then of course the final state variable between the CPU and GPU when either writing out or at the end of the runtime. But it just summarizes basically all the different comparisons, how many bytes were compared over time, and then how many errors it actually ended up tolerating. But nonetheless, also then listing our absolute tolerance that it was allowed to operate in. So this is an example of just running autocompare right out of the box to confirm that your GPU code is in fact doing what you think it should be doing and doing that effectively. Any questions there showing this particular exercise here? So I'm going to go ahead and follow this second question here. This, if you recall from the last exercise from when we were working with mini-weather, we had some issues with the tile clause where if we introduced it on a too large of a tile, then we'd actually get incorrect results. To note, this bug, as we end up finding in the NV Fortran compiler, is actually fixed in version 22.5 as what I've been told when it's released. And basically the issue that we saw from that last session is if we have a tile that's of size greater than 1024, i.e. greater than the block size that CUDA allows, it'll end up introducing errors and overriding values within each thread block, thus then producing incorrect results. So how about we try introducing that tile clause like we did before and seeing if we can see that similar kind of error using autocompare. So I'm going to change the domain size of this model to 1024 by 512 just to keep it the same as our last exercise from prior. And then I'm going to go into mini-weather here, and let's go to that kernel that we were working on before. We were trying out different clauses to see different optimizations you might try on that kernel. So the kernel we were looking at was the applying the tendencies to the fluid state here, and we could say try instead the tile 32, 32, num vars. So in this case, the size of the tile is 32 times 32, and the number of variables that we're processing within mini-weather are 4. So this is actually a 4096 size tile that will exceed the capacity of what the tile block is allowed to have for each distributed loop within the how the compiler splits up the work when you implement the tile clause. I think you still need tile loop there. If I'm wrong, the compiler will tell me that I'm wrong. So nonetheless, also let me make sure I edited the right one. Did I edit edited the OpenACC file, not the original file, so that's good. So I made that edit there. I don't have the minfo Excel flag out, so it's not telling us exactly what the compiler is doing at the moment. But nonetheless, if you can add that if you like, if you want to see exactly the change that happened. So now instead, when we add the PCAST compare clause here, we still have the ABS 12 here to ignore the basically the machine precision error kind of like scale of problems. But now we're actually starting to see like much more significant errors, as we see like already starting to be printed. And we're seeing that's actually happening within the state function here, or at least a state variable, when we get to the function output. So this is impacting the correctness of the code in another part of the model. You don't necessarily see that the error is in fact within the where we just introduced the error within the function that is semi-discrete step. But nonetheless, we can see that the error we just introduced, in fact, produced an error, and is much more significant than otherwise. We have these actual expected values of 0 when we don't expect a 0 value, and it's that's actually what you would see if we say try to visualize the output from that most recent run. So if we go say to our visualization software here, I'm going to restart the kernel on this just to get this going. But if you have not used this notebook here, this might be an easier way to navigate visualizing the output from AnyWeather than say NC view and an X session. So here at least it still like looks pretty normal. I think if I ran the model longer, you would see the error propagate further out, because I think the 2-second runtime is not sufficient to actually see anything significant. So let's just bump this up real quick. Let's do maybe I don't know. Let's do actually let's do just 20 and then 200, and then we can set the output frequency as 20. And just so we get like the close to 200 exactly, let's put 201 there. So I just changed the simulation runtime of that. We still have the error introduced from the larger tile clause and should be allowed. And let's rerun it with that longer simulation time. It'll take a little bit longer, but I don't think too much longer. Should be manageable. And we can then visualize the output and see if there's differences we can see beyond just the quantitative differences we see from PCAST, but then also within the visualization as well. And highlighting that, I essentially just want to focus on that. It's important to, if you want the quantitative comparison of validation, verification of your code, PCAST can achieve that, but you can also do a significant amount of validation just by looking at the visualized results of the model and seeing if it just looks right. If there's the movement of the eddies and the patterns within the fluid flow or whatever, say, project you might be working on. A test, quickly accessible visualization suite can also be just as significant towards enabling quick turnaround time in terms of verification and validation. This is taking a little bit longer than I was thinking in terms of the getting us through. Hopefully it doesn't time out. It might, but nonetheless, I'm going to go ahead and just, given we're at time, yeah, it is ball time. So I think I was too eager for how much time to spend on that. But just the final points to make. PCAST is not able to verify that the original CPU code is correct. Basically, you still have to rely on the fact that the software you're still starting with is relatively correct. You can do comparisons from one run to another or from CPU to GPU, but you can't necessarily use PCAST to ensure that the science itself is correct. So that's still that ownership responsibility is still on you, the programmer and domain scientist. However, you can use PCAST to verify that the CPU and GPU results are staying consistent, either using a golden file, across minor edits, or in fact using autocompare between and comparing the redundant operations and runtime between the CPU and GPU. PCAST can then also verify the results computed between the CPU and GPU are correct, but keep in mind that that differences sometimes can include some machine precision error, and so it's important to keep that in mind as you see, say, a large output from PCAST of small scale errors, but might not be significant for the particular problem at hand. And lastly, just goes with the theme of this particular tool. implementing some form of validation, verification, and development workflow is very important towards just not only for establishing your own trust in the fact that your software is working and doing what you're expecting it to do, but also, as you say, publish your software and make it available to other users so that they can do the same and trust in you that the work you've done and put forward towards making your scientific work trustworthy is in fact shareable and reproducible and again trusted by your colleagues within the scientific community. At the same time, if you navigate the process of implementing validation verification in an incremental and consistent manner, that will also help you just minimize creating bugs throughout the development life cycle. So having gone through all that, thank you for your time, and I'll take any questions. Thank you, Abhishek. I appreciate your time. Yeah, all these materials will be uploaded online. I'll probably send out an email just to double check the error that we encountered earlier on, but hopefully we can get that sorted out sooner rather than later. But yeah, and if you haven't completed the survey, feel free to please do that, and you as you have time available. That'd be really helpful to us in order to better serving you at future sessions.